Gas laws are mathematical equations that experiments have shown allow us to predict how an ideal gas will behave if the conditions of the gas change. The laws are the work of many chemists who determine the relationship among different variables. Robert Boyle determined the relationship between pressure and volume, and he has a law named after him, Boyle's law. It says that the pressure times the volume is equal to the new pressure times the new volume. So if we change pressure, that causes the volume to change. A man by the name of Jacques Charles developed a law called Charles' law that relates volume and temperature. Another man, Joseph Gay-Lussac, determined a law between pressure and temperature. And Amadeo Avogadro, of Avogadro's number fame, determined a law that related the volume to the number of moles of a gas. And that's the most obvious law. Really, if you have more stuff, it takes up more space. Now, fortunately, all of these laws can be put together into something called the combined gas law. The combined gas law is this great big monster equation right here. And it's really the only one that you need to know. Fortunately, it's also listed on the back of your periodic table. The numbers 1 and 2 represent two separate conditions. So P1 is the pressure at the beginning, and P2 is the pressure at the end. V1 is the volume at the beginning, and V2 is the volume at the end, and so on. One of the most important things that you have to remember is that the temperature, whether it be the first or the final temperature, must be in kelvins. You cannot use degrees centigrade in this calculation. So let's take a look at a Boyle's law example. In the example, a balloon of 100 milliliters of methane gas has a pressure of 780 millimeters of mercury. It now has a pressure of 760 millimeters of mercury. So what's its new volume? Well, we can start with the combined gas law, which is this, and we look to see which variables are changing. We see milliliters up here in our word problem, and also a question about the new volume. So volume is one of the things changing. We also see that we have a pressure of 760 millimeters of mercury and another pressure of 780 millimeters of mercury. So pressure is another variable that's changing. But which variables do you not see in the word problem? Which variables are not changing? Well, we don't have any moles up there, and we don't have temperature up there. So when we go to our combined gas law, we can just get rid of those from the equation. So we'll strike out N1T1, and we'll strike out N2T2. That means that the combined law just reduces back to Boyle's original law, which is P1V1 equals P2V2. Now you don't have to rewrite this on your worksheet. Once you've marked those out, you can just begin your substitution right there. I'll show you how to substitute right now. We'll plug in P1 right here. This is our 780 millimeters of mercury. We know that because it says that a balloon of this volume had a pressure of 780. So that's P1. We plug in volume 1 because it tells us that the balloon was originally 100 milliliters. P2 is in the equation, or in the word problem up here. It says it now has a pressure of 760 millimeters of mercury. And V2 is our unknown. So that's the new volume that we're going to solve for. So we plug these into the equation. P1 V1 equals P2 V2. And we need to solve for V2. We can do that by just dividing both sides by this 760 to get it by itself. And you can do that on your calculator. You don't need to rewrite it, but I'll show you what that looks like. V2 here is equal to 780 times 100 and divided by 760. Notice that we have millimeters of mercury on the top and bottom, so they cancel. The results are these milliliters right here. You don't have to worry about what the volume units are as long as they're the same. Whatever units are left over, those will be the units for your answer. When you multiply and divide, you end up with 102.6 milliliters. Remember that whatever units are left over, those are the units for your answer. Now for a Charles law example, we have a piston which has a volume of 310 milliliters full of xenon gas and a temperature of 58 degrees Celsius. It's then cooled to 15 degrees Celsius, and the question asks, what is the new volume of the xenon gas in the piston? So again, we start with our combined law, and now let's look at the variables that are changing. We see a milliliters up here, that's a volume, and it also asks about the new volume of xenon gas in the piston. So volume is one of the variables changing. We also see a temperature up here. It's in degrees Celsius, so we're going to have to convert that to Kelvin before we can use it in an equation. We also see 15 degrees Celsius, and we'll have to convert that. So we know temperatures are changing. But what are the variables that are not changing? Well, again, we don't see moles in this equation, and the other thing we don't see is pressure. So we can strike these right out of our equation. We get rid of pressure and moles, and that leaves us with just volume and temperature. So the equation is reduced to Charles' law. V1 over T1 equals V2 over T2. So we substitute in the variables. We have to figure out which one is which. The piston starts with 310 milliliters, so that must be volume 1. It also has a temperature of 58 degrees Celsius. We convert that into Kelvin, 331 Kelvin, by adding 273, and that's temperature 1. When we cool it, that's temperature 2, and the missing variable is V2, volume 2. So now that we've substituted into our equation, we need to solve it for V2. Now you can solve this explicitly for V2 and say V2 is equal to V1 T2 over T1, or you can cross multiply. And the way we do that is we start with the variables that are diagonal to the variable that we're interested in, V2. So these two we multiply together, and then we divide any numbers that are in the same diagonal here with the variable. And this is often called a butterfly. So these two numbers are multiplied, and then we divide this, and it equals V2. If we'd solved explicitly for it, it would look like this, but you don't have to write it this way if you don't want to. If you notice, there are a couple of units that cancel, and that's Kelvin here on top and Kelvin on the bottom. It leaves us with the volume of milliliters, so that's the units for our answer, and the answer is 269.9 milliliters. Avogadro's law is the example we're going to look at next. An aluminum can with 350 milliliters of nitrogen gas could hold 0.0158 moles of nitrogen gas. If the can was dented, it has a volume of only 74 milliliters. So how many moles of nitrogen gas can the can hold after it's dented? Well, again, we're starting with our combined law. We take a look at the variables that are changing. Again, we see volume, but this time we also see moles. We see 0.158 moles, so that's got to be N1. And then we have the question, how many moles can the can hold at the end? So that's going to be N2, and that's our unknown. So we're looking at an equation that has volume and moles in it. Which variables are not changing? Well, we didn't see pressure anywhere in the question, and we didn't see temperature anywhere in the question. So we can strike these out of our equation again, and we end up with V1 over N1 equals V2 over N2, the only variables that are left. So that reduces to Avogadro's law, which looks like this. Again, you don't have to rewrite it. What you've already got written down right here with the variables struck out is totally fine. We can substitute in now, and we know that the aluminum can started with 350 milliliters, so that's V1, and it ended with 74 milliliters, that's V2. It started with 0.0158 moles, so that's N1. And they were asking about how many moles it had at the end, so that tells us that that's N2. So we substitute like this, and we cross multiply. And we're looking for N2. So when we do our butterfly, like this, we start with the one that goes diagonally this way, multiply these two together, and then divide by this one, and it equals N2. If we solved explicitly for N2, we would have N2 is equal to this right here. So N2 is equal to N1 times V2 divided by V1. But we don't have to do that. We can just multiply these and divide by this, and it'll equal our N2. When we do that, we see we've got some units that cancel. This time it's milliliters. And moles are the only variable left over, so those are the units for our answer. And we find we have 0.00334 moles. Notice that there are three significant figures in this answer. Our given here had three significant figures, as did this volume. And this would have had three significant figures if I'd put a decimal point there, but we can pretend. And we have three significant figures in our answer. The last example is a combined gas law example. We have a weather balloon that's filled with helium gas on the ground where it has a pressure of 1 atmosphere. That's the typical pressure at sea level. And it has a temperature of 25 degrees Celsius. And the balloon has a volume of 2,180 liters. After it's released and rises up into the sky, it has a new pressure of 0.785 atmospheres, and its volume has expanded to 3,484 liters. What's the new temperature under those new conditions up in the sky in Celsius? Well, again, here we have our combined gas law. Let's identify our variables. P1 is our 1 atmosphere. T1 is 25 degrees Celsius. Now, remember that we need our calculated number to be in Kelvin to start with. So we have to add 273. We have V1 over here is our initial volume. Our final pressure, once it's up in the air, is P2. And our final volume is V2. And they're asking us for the final temperature, which is T2. So this is our unknown that we're solving for. If we do our substitution, we've got a lot of stuff. Oh, by the way, we didn't see moles in here, so we can get rid of moles in our equation before we substitute. So strike that out, since it's not in the equation anywhere, or in the problem. And then substitute. We get this great big mess here after we do the substitution, but we can still solve it the same way with our butterfly. We're going to multiply these two numbers, or all three of these numbers, and then we'll divide by everything in this other circle here, and that's these two. So we'll divide by 1, and we'll also divide by the 2180, and that'll give us T2. We could solve explicitly for T2, and we would see that we have V2, P2, T1 divided by P1, V1. When we plug all that in, we can cancel liters, and we can also cancel atmospheres. And the only variable left over is K, which is temperature. So that's the units for our answer. Our answer is 374 K. But remember, back up in the question, it asked for Celsius. It gave us Celsius for our initial condition, so we should return our answer in the same units, Celsius. So to convert Kelvin into Celsius, we need to subtract 273, and we end up with 101 degrees Celsius.